Thank you. I'm Brad Beebe with AWS, and I'm the Principal Product Manager for Amazon Neptune. And today, we're very excited to give you a deep dive on Amazon Neptune. Before we jump in, I wanted to give you a quick overview of what we're planning to cover today. We'll start with a little bit about how you build applications over highly connected data and why is this important. Then move into some of the different types of graphs and give examples about how to query them. And then we'll work through a use case for property graph, as well as an RDF knowledge graph example. And then we'll give you a little bit of a peek underneath some of Amazon Neptune's fully managed enterprise features. So today's applications need to process data that's both rich and highly connected. The data is rich in that it's coming from many different sources. It has heterogeneous data elements and data attributes. And it's the connectedness of these data elements that really enable new applications. So if you think about a social network, for example, it's the interactions of individuals with different content or relationships between them that really provide the value for the network. And similar types of things in recommendation systems. In retail fraud, it's relationships such as shared accounts or shared payment mechanisms that provide the value in being able to build these applications. One of the things about rich and highly connected data is that it's particularly well suited for a graph representation. And there's a number of different use cases for highly connected data and graph representations. We talked about social networking. There's also various different types of recommendation systems. Knowledge graphs are a type of application where you use a graph representation to model information and then enable customers to help improve their retrieval or answer questions about data. Fraud detection applications. The life sciences is a rich space for graph applications, both ranging from drug discovery to data integration to precision medicine type use cases. And then, of course, network and IT operations are fundamentally graph structures. And so they map very well into these kinds of structures and relationships. So let's look at a couple of examples. Here we have a recommendation graph, and it's showing individuals, relationships between them from a social network context, relationships from a transactional context, for example, individuals purchase products, and also some interest models. And so we have people there that follow particular sports. And by representing this information in a graph model, we can start to make recommendations. And so we can say things like, people who also follow sports purchase this product. And so we can recommend to this user a product that other people like them, did purchase. Similarly, we can do something for social networks. We can make a recommendation based on a shared friendship relationship. As I mentioned, a knowledge graph is a technique where you use a graph structure to represent information and facts that you know. In this case, this is an example taken from the World Wide Web Consortium or the W3C's knowledge graph webpage and augmented for this presentation. But we have a picture of famous artwork, the Mona Lisa, the museum where it's located, some information about the city overall, and then we have some information about users and some travel history. And by representing this information in a knowledge graph, we can start to answer questions for users like, who painted the Mona Lisa? What museum should Alice visit while in Paris? What artists have paintings in the Louvre? We're very excited that Thomson Reuters is participating in the Amazon Neptune preview. This is an example quote from them about their use case. What they're doing is they're helping customers to navigate very complex sets of tax policies and regulations. And they're using a graph-based approach to be able to model these regulations and help customers understand how they apply to them. And so this is a very, very interesting use case that we're seeing. So we've seen some of the types of compelling applications that you can build over highly connected data. So what are the types of database systems that you can use for this? Well, you could use a relational database, but there are some challenges. Relational databases are generally designed to process information that's highly structured and changes relatively infrequently. This query language for a relational database is SQL. If you use it to process relationships in your data, you end up having to use a large number of joins in your query. And this makes queries both cumbersome and awkward over highly connected information. The second reason is that the types of I/O demands for relational workloads versus graph workloads are very, very different. And relational databases just aren't optimized to efficiently process graphs. And the third thing that we see in graph applications is that customers often want to bring together data from many, many different sources. And so they want to be able to flexibly ingest and accommodate data that they didn't initially design the application for. And this is a little bit challenging to do in a relational database. So let's look at a specific example about how these models differ. On the left-hand side, you'll see a fairly typical entity relationship type diagram that was designed for an HR system in this example. And it was really purpose-built to support HR business processes. And you can see it looks as you would expect in a relational model. You have foreign key relationships and so on. On the right-hand side, we have a similar model represented as a graph. And here we see that the relationships themselves are first-class objects. And so if we want to ask questions that we hadn't anticipated, so for example, what are the skills that are needed to build a particular product? To do that over the relational system would be a very complicated and complex SQL query. But to do that over the graph would be a fairly natural expression. So it's really about the models and the way that the models enable you to ask questions over the data. So what's a graph database? Well, a graph database is a database that's optimized for the storage and retrieval of graph data. It supports specialized query languages and APIs that are optimized for graph, and it's tuned for the types of I/O characteristics that are required to efficiently process graph applications. There's two leading models for graph. The first is something called property graphs. And a property graph has nodes and edges and node properties and edge properties. And the leading framework for processing property graphs in the open source is something that's called Apache TINKERPOP. And it provides something called GREMLIN, which is an imperative language that lets you express traversals over your graph. So A is connected to B, has a particular attribute. The second major framework is something called the Resource Description Framework, or RDF. RDF is part of a set of World Wide Web Consortium, or W3C standards, collectively known as the Semantic Web, and it has a query language for RDF, which is called SPARQL. So as we were designing Amazon Neptune, we looked at some of the alternatives in the graph database space. And what we found was that customers often had challenges scaling up. And so it was relatively common that customers would try a proof of concept or a prototype application and have quite a lot of success with it. But when they tried to operationalize or put it into production, they experienced a decline in query performance or operational difficulties as they tried to scale up. The second thing that we found was that customers had a lot of difficulty in building and maintaining high availability configurations. So when they wanted to take these applications into production, it was challenging for them to set up and configure HA features. Further, these kinds of feature sets were not available in community or open source editions, and they required customers to license the enterprise editions. And then finally, what we saw is that, well, there are a number of products that support both the property graph and the RDF model. They tended to do so with a strong bias for one or the other. And so they didn't give customers the choice to choose the right model for the right application. So with that in mind, we designed Amazon NEPTUNE. Amazon NEPTUNE is a fully managed graph database service. Amazon NEPTUNE is fast. It's designed for graph applications that need to have very high throughput query answering with low latency. So you can query billions of relationships with millisecond latency. Amazon NEPTUNE is designed to be reliable. We offer multi-AZ high availability. We support horizontal scaling through read replication. We support encryption at rest. And so we have the set of enterprise features that you really need to put a graph database into production. And it's easy to use by supporting the most commonly used graph models, the property graph model and the RDF model, and providing support for the GREMLIN language and SPARQL. We make it easy for you to use open APIs to access the power of Amazon NEPTUNE. This is a quick view of the high-level architecture of NEPTUNE. So if you look across the top, you'll see some of the key use cases for highly connected graph data. Then moving down the stack, you see the open source and standard APIs for property graph, TINKERPOP, GREMLIN, and RDF and SPARQL. Then below that, you see Amazon NEPTUNE. Amazon NEPTUNE is a purpose-built high-performance storage engine that's optimized for graph. It's durable and ACID and provides immediate consistency. In addition to the standard and open source APIs, we also support APIs for managing the database. And in particular, we offer a fast parallel bulk load of data that you have stored within S3, in addition to other database management functionality. And then moving along towards the bottom of the overall architecture, Amazon NEPTUNE rides on a cloud-native storage service. And this is what gives it the ability to offer these sort of enterprise features for HA, read replication, and encryption at rest. So now that you've had a little bit of background about NEPTUNE and some of the applications, let's look at different types of graphs and how to query them. So you'll recall that the first model we talked about was a property graph. And this is driving down a little bit more detail. You can see in a property graph, the nodes or vertices can be used to represent sort of the core pieces of information. And then they can have different attributes. In this case, in this example, we have a node that has a type user, and which is also called a label. And then that node has an attribute, in this case, the name, which is called Bill. Then we have a second node or vertex. In this case, it's also a user named Sarah, and there's a relationship between them. In this case, the relationship also has a type, which is called friend, and there's an attribute on that, which is the date of the friendship. And so this is an example of a property graph relationship. Now, how would you create this kind of graph using Apache TinkerPop? And so here we're looking at Apache TinkerPop version 3.3, which is the version supported by Amazon NEPTUNE. And you'll see an example here looking at sort of the Java binding of creating a vertex for user 1. Then we create a vertex for user 2, which is Sarah, and we add the edge. And the resulting graph is what you see there on your right. So the second model, as you'll recall, was the RDF graphs. RDF graphs are really described as a collection of what's called triples. A triple consists of a subject and a predicate and an object. And so in this case, the subject is something called an IRI, or an internationalized resource identifier, which provides a unique identity. Here we have the example of the type of the node, which in this case is user, just as in the previous example. And then moving down, we have an attribute or a property here, which is the predicate contact name and gives a bill. And that set of triples, or that triple, describes the node that we see on our right. Now, the third position in the triple, the object, can be either an IRI or what we call a literal. A literal in RDF is very much like a property, and the types of literals that you can have correspond to the XML data types. And so a literal would be a string or an integer value. You can also have in the object position an IRI. And when you have an IRI in the object position, it forms what you would think of as an edge in the graph. And so If you look across the bottom, you can see that I want to create a friend relationship between person 1 and person 2. And I express that in a triple, where in the object position, we have an internationalized resource identifier, or an IRI. So if we expand this example to the full graph we looked at before, you can see how we would form that. So across the top, we have a triple that defines, or a set of triples that defines the node Bill. You can see the IRI identifying as person 1, a statement identifying the type as a user, moving down the property with the predicate name Bill. The second triple describes the relationship, the friend relationship, so person 1 with the predicate contacts friend to person 2. And then the third set of triples on the bottom describes the second node for Sarah. And so this is an example of how you would build the same graph in RDF. So going back to looking at relational versus graph modeling, in this case, let's take more of an order system. And so on the left-hand side, again, you see a relational model, an entity relationship type diagram. And on the right-hand side, you see the graph model subset of that. So this would be the equivalent information represented in a graph model. And so let's go through and look at some query examples for the differences here. So most of you are likely familiar with SQL. We want to ask the question here, find the name of the companies that purchased the Echo. And so as we go through, we're joining across from the customer table to the orders table to the order details and ultimately to the product. And then we do a filter on the product name Echo. So this is a fairly standard SQL query. Now, if we look at this in SPARQL, which SPARQL is the declarative graph query language for RDF, rather than expressing the joins as you would in SQL, what you express is a set of triple patterns. So recall that RDF is made up of triples. And so here, the first thing is we express a pattern for the customer and the order. In SPARQL, the variables that start with the question mark are used across the triple patterns to be able to create the equivalent of the joins. In the next line, we go through and look at joining the order to the order details. And then finally, we have a filter on the product name. And so this is the SPARQL example for answering the same question about find the names of companies that purchased the Echo. Now, GREMLIN provides an imperative traversal language for property graphs. And so to answer the same question, find the name of the companies that purchased the Echo, in GREMLIN, we're going to do it as a graph traversal. And so first, we start with the product. So we find all of the vertices that have the label product. Then we filter on the name, and then we start traversing the graph. So we go out to order details, to order, to customers, and then we find the unique company names, deduping at the last step. And so you can see the differences in each of these different graph models, but how you can use them to answer the same kinds of questions. So let's look now specifically at a property graph and Apache TINKERPOP social networking friend recommendation example. And the technique that we're going to use is something called triadic closure. This is very similar to triangle counting. A triangle is the smallest fully connected subgraph in a graph. And so the idea here is that if two people have a friend in common, but there's not already an edge between them, that would represent the opportunity to create a new triangle in the graph. And it could be a recommendation. And so this is an example of a triangle. It's a fully connected subgraph where everyone knows each other. But let's see if we can find some opportunities to create these triangles and make new recommendations. So first we start with Terry, and we go out to find friends of Terry. Then we go to find friends of Terry's friends. Next, we see that there's not actually already a relationship between Terry and Sarah. So this represents our opportunity to make a recommendation. So we've looked at this graphically. Now let's look at it through a Gremlin traversal. Here's the overall traversal, and let's go ahead and step through it. So first we find Terry. Then we find friends of Terry. Then we go out and find the friends of the friends, where there does not already exist a friend relationship. And so this is an example of how we can use Gremlin in a property graph to implement a very basic recommendation mechanism using triadic closure. Now let's take a look at an example using an RDF knowledge graph. So you'll recall that one of the features of RDF is that it uses these IRI mechanisms. And so in this example, we're going to look at some information that represents companies and geographic locations. The company information is taken from something that Thomson Reuters provides, which is the PermID data sets. And then the geographic information is taken from something called GeoNames, which is a publicly available data set of geographic locations and code sets. And so here in this first example, if we look at the triple that we want to say this particular company, we see the URI for the company, and we'll see later that this is actually Netflix, has an incorporation relationship with a country. So Netflix is incorporated in the United States. And this triple is how we would express that. Now there's a couple of nice things to note here regarding RDF and the URI or IRI formats. In particular is that the standardization and the use of these identifiers helps you to interchange data with external systems. And so that's one of the features that we see frequently across RDF applications. Now, to take this example a little bit further and look at it as just the single triple, you'll see here we have the again, the same statement shown. Now we want to look at adding the property. You'll recall that properties in this case are literals in RDF, which are the XML data types. And here we can see that this is how we're expressing the name of the company. Now, if we look at this example as a full set of triples, we'll see the first set of triples at the top, which represents the incorporation information. The next set of triples, which describes the name attributes. In this case, we're also adding phone number information, and we're pulling in the ISO 3166 country code at the bottom. So I mentioned the benefits of using IRIs or URIs. And one of the things that this enables you to do is to create what's called linked data. And so this is where you have different data sets that are owned and managed by different organizations, but you can use them to create new applications. And so in this example, you saw that we were using the GeoNames data set to represent geographic information. And we can also include things like Wikidata, which is the structured information from the Wikimedia Foundation. And by using these IRI concepts, we can guarantee the uniqueness and identity of the different data elements, and we can easily use them to bring things together. So let's look at some examples of querying this kind of data. So you'll recall that SPARQL is the query language for RDF. It's a W3C standard, and it's a declarative graph query language. Here, we want to first issue a SPARQL query finding the name of a particular organization with the URI. And so in this case, you'll see the select statement up top, and you'll recall from the order example that the variables in SPARQL start with the question mark. And this query results in the name of the company, so it's Netflix. Now, if we want to expand this out, and we want to look at all of the properties and their values, or the predicates and their values, we can do this kind of triple pattern, which you see at the top. So we have the URI, and then we have two variables, the property and the node. And this results in all of the triples about that IRI. So we can see the name, the phone number, and the location. And you'll recall that the location, the object is an IRI itself, and so that can be further dereferenced. Now, suppose we want to find the phone number for the company named Netflix. We can also express that as a triple pattern in SPARQL. So again, looking at this query, you'll see that there's the organization named Netflix, and we want to find the phone number. And so this returns both the IRI for the company that named Netflix, as well as its phone number. So switching gears briefly, let's take a look at some of the enterprise features that Amazon Neptune has. Amazon Neptune is a fully managed service, and this means that you can operate and deploy it completely via the console. You can configure multi-availability zone high availability. You can configure clusters for read replication. Amazon Neptune supports up to 15 different read replicas. You can configure both encryption at rest using customer managed or KMS keys, as well as encryption in transit. And you can manage all of your backup and restoration and point-in-time operations all through a very easy to use console and API interface. So as an example of deploying Amazon Neptune supports deployment inside of a VPC or a virtual private cloud. The private cloud must be configured to a network that has at least 2 subnets in different availability zones, and this is how we can achieve the high availability. And the cluster volume always spans 3 different AZs to provide you durable storage. There's a link included at the bottom of this slide that can provide you more details as you go through and try and set up Amazon Neptune. So let's look a little bit about Amazon Neptune's read replication capabilities. So one of the things that Amazon Neptune does for you automatically is it detects database nodes when they're failing and automatically replaces them. It replicates information across multiple availability zones and provides you a very, very low latency replication and very fast failover. This allows you to quickly scale out reads across of your clusters. In Amazon Neptune, failovers are typically less than 30 seconds. This is an example of the model of a failover. Starting from a database failover, within 15 to 20 seconds, the failover is detected, the recovery begins, and then your application is back and running in typically less than 30 seconds. So Amazon Neptune is now available for preview. It was announced at reInvent, and we've started onboarding customers. You can sign up for the preview from the web page, which is listed below. Or if you just visit the product page for Amazon Neptune, you'll see a prominently displayed link. And the documentation for the service is all publicly available. We'd love to hear from you, and we'd love to have you try out the service.